Welcome, everybody.
Howdy.
Good evening. Well, tonight is chapter 4D, and I don't know what we're going to do when we pass Z for chapter 4, but we'll have to figure out something. ZA, ZD. Well, let's start with prayer. Father, we just pray that you help me get through this. Just help everybody to learn. We've got all kinds of people, we've got all kinds of learning styles, and we've got all kinds of interests. And I'm doing my best to present material that will work on everybody. Anyway, in Jesus' name, amen. All right. Let's start reviewing. Oh, last week I started talking about diodes and diode junctions. Remember, and I said current will flow one direction, the whole will flow, but it won't allow electrons to flow the other way. I had it totally wrong. I was so confused. Actually, if the arrow is pointing this direction, that means that's conventional flow, that's whole flow. Electron flow is going that direction. So if we go to this next one now, people were actually going to get in this later in the course when we start talking about power supplies and how they work. But you can see a diode here, and whole flow goes this direction from left to right. That is how it is up there, right?
Yes.
Electron flow cannot go that direction. So when you got AC current applied, see this line here? And we haven't got into AC yet, but if you start out at 0 volts and then start going toward the positive, that's one direction. But as the signal goes under 0 volts, it goes in the negative, that's going the opposite direction. That's called AC, alternating current. So if you applied AC to this capacitor here, nothing would happen. But by putting a diode in here, only the positive side, that's represented by these loops here, the dotted lines, will be on the positive side, and it'll charge this capacitor here in a positive sense. So there will be electrons built up here, and there will be holes built up on this side, giving this a positive reading. And then over here, we've got what's called a center tapped transformer. And with that, you can use 2 diodes, and instead of just getting one and then another, you get all the lumps just going like this, and they're a lot easier to filter out. But that's something we're going to get into a lot more detail, but just for the purpose of getting you familiar with some of the things that we're going to be talking about.
That is worse than I thought.
What's worse than you thought?
My eyes don't see like they should.
Oh, Bruce, why don't you come on up here?
You want this seat here? No, why not? Right behind you, I can find.
Now,
Compromise.
the next thing is
He's got the control.
now remember I was talking about this thing here
Yes. Yes.
and how these fuses,
We're in the wrong place.
yeah, they're in the wrong place, because if these ends are hooked up to a battery and it shorts here, it's going to burn up the whole wire. And we've seen enough cars actually on fire because something went wrong. I mean, they actually got to the point where if you have a collision, it turns off the battery pump. I mean, the fuel pump, to keep it from pumping gasoline into the fire. You don't want a fire in your vehicle, because of something like that. So the fuses should be at this end.
Next to the battery.
Now that I've shown you that, I can go back to oops, not that, not that. It's moved. Now, notice this fuse holder. That's a pretty standard automotive style fuse. And I'm going to show you a video here of me installing these on Willie's truck, which now happens to belong to Bruce.
Well, of course it does.
Now that
It still
fuse,
runs.
if you notice the trying to get this out of my way here. If you notice these contacts here, they're big, heavy, quick disconnect connectors, and they fit on.
Ooh, what happened here?
I accidentally clicked. So these fuses will take a lot of current, and they will not drop your voltage nearly as much as this other style of fuse. Because you don't want, and 12 volts, if you lose a half a volt, you're down to 11.5 volts, and your radio is barely working. So, and here I'm gonna show you this video and then make some comments later. Okay, now we're going to fuse both sides of this line, and we're going to have one side long and one side short. So I'm going to cut that off there and take this and cut it off here, which is nice of the manufacturers to put a loop there so that we can do that. Now I'm going to get all of these trimmed and ready to go. By the way, Willie's filming so that we can just put terminals on. Now this is number 12 wire I'm working with right here, but it's a short distance and there won't be much loss. But this here's number 10. But these connectors here are 10-12, so they'll work on both. So what I want to do is get my good crimpers, which is right here. Get it loaded in here. Oops. Okay, there we go. I have this is shrink tubing that's on here. And I need to, there we go, we're up in there. Okay. All right, that was all the video I had. That I wanted to do that. Remember Willie, who made it possible for us to have this room. Anyway, there's a number of things I want to talk about. One is the length of the wire in the battery terminal. The reason I wanted them short is to ensure that those wires could not short onto anything between the battery and the fuse. And in that situation, I needed them to be short. Actually, you can buy boat standards, you can have up to 18 inches, but you want to make sure that there's no way for that wire to get shorted. Because if it shorts, that battery can put out 1,000 or 1,500 amps, and that wire will immediately go up in flames. And it's not a pretty thing. So I talked about shrink tubing. Shrink tubing is some tubing, you slip it over the wire, you apply heat, and it shrinks to the wire. And the kind that I like is the kind that has glue inside of it. So that as it shrinks, the glue melts and seals the connection. And that way you make sure nothing can get into the connection. Now, you might have noticed that the cable was white. I wonder. No, that's not what I want. Okay. Now. Oh shoot, that does not work. Ah. Okay. Now, we're going to fuse both sides of this line, and we're going to have that white wire. Yeah, that's actually marine cable. The wire that's inside is tinned copper. When you use tinned copper with a tinned terminal, you need not solder it. It will not corrode. Because when you make a proper crimp, it anneals the wires together. If it were standard automotive cable, which is okay to use, but standard automotive cable has an outside jacket on it, and it's usually gray. And the copper, the wire is just copper. It's not tin. So when you put copper with tin, those are dissimilar metals, and they can corrode. It takes a fairly rough environment to do that. If you live out in the desert, you never have to worry about it. But living here on the coast, that's something that you got to make sure that you take care of. So if you're using untinned wire, be sure that you solder it as well as crimp it. And never just solder a wire that you're using for a battery cable or something number 10 and up. Because if you just solder it, it comes loose and the terminal gets hot, the solder just melts and the wire falls out of the connection. It's not a pretty thing. Anyway, a fair amount of experience in that. Okay, let's review Ohm's law. Now, we talked about potentiometers or variable resistors. In here on the left, you can see a potentiometer. Some of us might think of that as a volume control, and a lot of pots like that are used for volume controls. There's a trim pot that's the blue one there. And I like this one because right here you can see how it functions. You've got a wiper here, and this part that goes around here is the resistive part of the arm, and that's usually carbon that's on there. And then this wiper rolls around, and you change the resistance, and its schematic symbol is this. So right now, if this is indicating in the middle, this arm here would be in the middle. If this arrow were down here, it would be over here. And shoot. Now, what I want to do is actually show you one. Here is a potentiometer. I've already see these tabs here on the side. These tabs hold this rear panel on. And so I can just now remove the rear panel. And if you remember the diagram, there's a swipe, and that's these two copper terminals right there. And this is one side, and there's a resistor that goes all the way around here and comes out this side, and the center one is connected to the center tap. And as you rotate it, you change the resistance. This is a 500K pot, and I'm not going to bother using my ohm meter, but you get the picture? Somebody say yes.
Yes.
Oh, yeah.
Oh, thank you. Okay. Okay, we talked a lot about the current flow in parallel and series circuits. Oops. Wait a minute. This is another diagram of Kirchhoff's law, which I mentioned. You don't have to remember his name. But if we start over here, on this side, we've got three resistors that are in
Series.
okay. And what is I times R? What does that give you?
E.
Correct. So if you take IR of 1 and IR of 2 and IR of 3, you take the voltage, the voltage, and the voltage, and then you subtract the source voltage, it should come out to 0. So you got a battery here or a voltage source, and then all of these that are in series should add up to the same voltage. And if they don't, call a few scientists and invite them in, because you just broke all the laws that God has made, and somebody's going to be unhappy. So anyway, the next one is resistors that are in parallel. I wish they had, instead of going like this, they had gone like this. Because that's actually what the current is doing. And then with this one, it's going like this. And then this one, it's going like that. So I, which is right here at this point, is I1 plus I2 plus I3. So the sum of all of these will equal the current, which is I, remember. So IR is what?
E.
E, the voltage. IR equals IR IR3, the current in each one of these times the resistance equals a voltage. And the voltage in each one of these places from here to here is going to be the same. Which, by obviously just looking at it, we should know that, right? I will let that go. Okay, moving on. Remember this guy here? Somebody, and I like answering questions when I can. Somebody said, well, what about these resistors? How did you determine what they are? And the answer was, I just made them up. Let me delete a couple things. Oops, no, wait a minute, come on. I'm going to cut that wire. I'm going to close this. I'm going to restart it. Okay, now I come back over here. Now I'm going to look at the voltage coming in, and we can see that's 5 volts. And if you remember this point here, I had 2,000 ohm resistors, and I figured I'd get it close to 1.5 volts. But as it turned out, it was about 1.3 volts. So I changed this resistor to 500 ohms, which now is the blue line at 2.6 at the bottom of the screen. The bottom, I'm going to make 0. There. Now the top is 5 volts, that's the green. And then we got this point right here is just about 2.5 volts. So this point right here is 1.8 volts,
that
Which
because
is-
of the loss from the PNP
Yes,
or
and here because,
NPN.
yeah, because of the amount of the low drop in current, it's showing 9/10 of a volt drop. You can usually figure about 0.7 volts. But now what I'm going to do is I'm going to come over here, draft wires, and I'm going to, this signal right here. Well, hang on a moment. Actually, I'm going to do something else first. Let's take a look at this point here. Notice this line, this is 60 cycles per second. And it's about 1.7 volts. And that's the signal on here. And if I go here, it's right in exactly the same spot, but that's after the capacitor. So I'm going to hook up with a wire. I'm going to hook this capacitor up to this point right here. Now, when I go to, no, don't do that. There we go. When we go to this point, we have the same thing. We've got, shoot. We've got this AC signal driving the base of this transistor. Now, if we go to the output here, we hopefully should see this amplified. But watch. Oh, wait a minute. Nope. So you're going to make a liar out of me?
Either that or you blew the transistor.
Good way to go.
Chuck said I blew the transistor. Why is this not working? Oh, shoot. Okay, well, I honestly, folks, I think I'm wasting your time. It's DC, it's not hooked up.
Perhaps you could just tell us what you were trying to show.
A picture's worth 1,000 words. And I think it would make no sense to you if I tried to explain it. I know what to do. There. Now that's there. That's node 02. Notice that it's not a pure sine wave. This is what the input is, and this is the output. Notice it's all just hammered. That's not how it should look. And that is because this resistor here is the wrong size and I need to change it. But I suppose I'm showing you this for those who like to build things and experiment. You could get this program and learn how to use it. You might ask me to teach you because it took me probably 3 or 4 hours to figure out how to make it work. But if I go to here, no, I thought I could close that one. Well, well, anyway, but if I go to this spot right over here, which makes it an emitter follower, which is some of you know, you can see that we have this blue line, which follows the input very precisely. But this has a much larger current gain than what's over here. But anyway, there's something to play with. I just, someday I'll make this thing work and I'll show you how it works. Now hopefully all of you remember this. these are our various power sources. Again, just for repeat, here's a large dam provides AC power to our homes. We use a power supply like this one. The Astrons are excellent power supplies, but that provides voltages to our equipment to operate it. Here's a battery which can also provide power to our equipment to do it. And here are a couple symbols for power sources. Here's a battery and here's a power source. This could be either AC or DC. And of course, here's a schematic representation. And of course, here are a couple AA batteries. And then I love this one, the potato battery. So moving to the next. If you remember this, let's talk about Ohm's law again for a minute. Voltage is the power that tries to push the electrons through or the holes through the wire. Either way, whichever way you want to look at it. And here's 4 amp being shoved through this restriction being caused by Ohm. Here quickly, I'm going to have another definition of resistance that might help you understand what's going on. So I want to show you this again. This is John showing us on the left-hand side, you have a voltmeter, and then you have the resistance in the middle, which John is increasing for us. He squeezes it off until there's just a little drip on the right side. So that might be a million ohms, and then it gets less and less until it's flowing like it's just a wire. And we'll show you again. The voltage is staying pretty constant on the left. And then the resistance is increasing in the middle. And after you get a certain amount of resistance, you can see the current on the right-hand side starting to drop off. Now, coming up here very shortly is another view. We're going to have the resistance just running open. And we're going to have the voltage on the left-hand side drop off. Now watch it drop off and what happens to the flow. The flow drops off. And I just repeated this 3 times so you can see it. As the voltage drops off, the current drops off. All right, Ohm's law. You all recognize this now. How many of you actually went out and found your own version of this online and copied it to your computer? Anybody out there? Well, I'm going to ask you again, go online, search Ohm's law, do the picture one for images, and pick out one of these that you like. Because you're going to need it. Unless you happen to be one of those people that know that I equals E over R, then you can algebraically figure out the rest of them. Can you do that, Ann? Oh, Ann can do it. Oh, good for you. You're like me. That's the only way I can remember it. I can't memorize these things, but anyway. And then there's this one, which I like because it shows them all. So moving on, let's talk again about Ohm's law and power. Now here is a definition of resistance. It's the opposition to the current by conversion into other forms of energy, such as heat. And that's all resistors do that. It takes the energy and it turns it into heat. That's why I talked about all the resistors and their different power levels. So you want to make sure you remember how we burned up a resistor last week. I mean, that was lots of fun. Anyway, moving on. Now, there's another thing about resistors that we need to know. And that is the percentage of the resistor. It used to be that it was the most common resistor had a value that was within 20% of what the value was on the resistor. If it's at 1,000 ohms, it could have been 800 ohms to all the way up to 1,200 ohms. And in a lot of applications in tube circuits, that's all the accuracy that you needed. But if you go to a 10% resistor, then it would be from 900 ohms to 1,100 ohms. If you go to a 5% resistor, the resistance could be within the range of 95 ohms. Oh, excuse me, I'm using 1,000 ohms. 100 ohms, you 95 to 105 ohms. I'm doing all this stuff in my head. Now, the resistors that I sent out in your package are 1% resistors, which are very, very accurate resistors. And they could be from 99 to 101 ohms, and that would be within its range that's specified. There are, on a normal resistor, there's 4 bands, unless you got a 1%, then there's 5 bands. But the first 3 bands are, the first 2 are its value. The third one is the multiplier. And then the fourth one is its accuracy, its percentage. So if it's blank, it's 20%. If it's silver, it's 10%. If it's gold, it's 5%. And brown is 1%. But the brown one will have 5 stripes. Three for the value and 1 for the multiplier. Now, something else that are probably, you've heard me talk about these things. These are the electrical quantities. I've talked about volts, ohms, and amps. But I've also talked about millivolts, kilovolts, regular volts, milliohms, megohms, kiloohms, you know, all of that stuff. And unless you have some idea of what I'm talking about, it's not going to make any sense to you. But let's just start with volts. Most things are measured in volts, and we have these little power supplies that we've built out that put out 5 volts. And there's a 9-volt battery hooked up to it. But I'll tell you something, I built an amplifier for Dave Sanford, N7TEE, that has 2.5 kilovolts driving it. You get wound up in that, you're going to be dead. But then I showed you lightning strikes, right? Tens of millions of volts, megavolts. There's also millivolts. Most of your microphones are in millivolts, about 5 millivolts, very, very low voltage, but also microvolts. Microvolts, hopefully, Lord, we get time here today, we'll get to see my display that shows an S9 signal on this radio that's sitting over here to my right. And that's in microvolts. An S9 is 50 microvolts, which is a tiny, tiny voltage. So let's talk about ohms. We talk about 10 ohms, and we've been using 100 ohms for our project so far. We've added 3 in series and had 300 ohms, and we've had 3 in parallel and ended up with 33.33333 ohms. And every once in a while you talk about milliohms, and that's if you're trying to measure the resistance of a wire like I showed you earlier. That's in milliohms. 1,000 milli means 1,000th. And there are megohms. And our meters that we've been showing you, their input resistance is 10 million ohms. We'll be discussing that more later. And then there's current, same thing. There's amps, which is actually a fair amount, but around the house, when you got 120 volts, you plug in a normal light bulb, 100 watt, it's about 1 amp, actually 0.8 amps. If you turn on your microwave, it's drawing 12, 14 amps from the circuit, which is a lot of current. It's put a lot of that power into the food. There are microamps, which are little tiny currents, and they're real common in the radio field. So anyway, micro is 1/1,000,000th, milli is 1,000th, and then you've got your normal, whether it's volts, ohms, and amps. Kilo stands for 1,000, so it's 1,000 times 1, whatever. And then there's mega, which is the big M, and that's 1,000,000. So when we're talking about this stuff, hopefully you will start catching on to what I'm talking about as we go through this. Now, about watts. Watts is not a place in Los Angeles. Power is everything. We talked about power. Power is the heat that's generated in a resistor. You got a voltage across it, current will pass through it, and as the current passes through, it generates heat. Your power supplies that are in your shacks, they produce power. Usually it's 13.8 volts and hopefully up to about 20 amps, because your transceivers, if you got an HF transceiver, draws about 18 amps when it's putting out 100 watts. So if you take somebody quickly, 12 times 18. Well, 10 times 18 is 180.
36.
Plus 36.
216?
216, right. 216 watts is going into a radio so that it'll put out 100 watts. Your radio's losing 116 watts in the process. But that's what it takes to generate a proper RF signal. Power is the radio signal that's radiated from your antenna when you transmit. And it consists of an electrical field and a magnetic field. When it hits the antenna, it turns into a current, which has an associated voltage with it. So and that's in, remember our strong signals, 50 microvolts, 50 millionths of a volt. And many radios are, in fact, most radios are good to below 1 microvolt. So your anti-talkie, 5 watts maximum typically, although there are a few that do 7 watts. Okay, power. Power is actually the current times the electromotive force. But remember, electromotive force is measured in volts. So a lot of your, if you've got old stuff, it's going to say E. And I always remember Ohm's law as I equals E over R. Electromotive force over the resistance. Or I times V, power, is the current times the voltage. And this is something else that you should have gone online and got your own version of, so that you can have it for yourself. Print it out and keep it in your notes, or have some place where you can access this. But with this, you can figure out the formula for E or voltage, R for resistance, I for current, or P for power. And if you remember anything about algebra, if you take I for E for shoot. What am I trying to do?
Substitute?
Yeah, I'm trying to substitute, but I get myself confused here.
What, E for me?
Oh, yeah, E
IR.
is R times I. So if you look at the power formula there, you end up with, if you replace E with RI, you end up with R times I squared. That's how that works. Yeah, I'm getting rusty. Okay, odd values in series. Darren, hopefully here in a little bit, will in his illustrations show us adding these up. But now,
What's the little T mean?
total,
Oh,
our total. Oh, you are so observant. So if we want to know what the total resistance is, and we've got multiple resistors in series, I mean, if we took 100 ohm, a 50 ohm, and a 20 ohm resistor, the resistance total would be
170.
100. Oh, good for you guys. So if we go and we look at this though, now this is a little bit harder to deal with. If you have two resistors in parallel, you use this formula and you can figure out what the total resistance is.
What does odd refer to? Two odd values.
R1 and R2 are not the same value.
Well, so
So if we had a 100 ohm and a 50 ohm, that would be a R1 times R2, which would be 5,000 divided by 150, which would give you what? Doesn't matter.
Yeah.
That
Gives you a
much.
number.
Darren's actually going to figure this out later.
Darren's going to illustrate. Joe's going to figure it out.
I have a calculator.
You're going to use your own meter to check its value,
Yes.
aren't you?
Absolutely. Yes, sir.
Oh, yeah. I'm sure glad to hear that change in attitude. Yeah, somebody appreciates my humor.
33.3.
33.3 ohms. Correct. And then we have this now, odd values. In other words, they're not, before we've had 100 ohms and whether we had 3 in parallel, so that's 100 divided by 3, which is 33.3 ohms. Oh, what if we had a 100 ohm, a 50 ohm, a 20 ohm, and a 10 ohm? That's 5.56 ohms. Now I want to tell you guys something. You can figure this out. You can take R1 and put it in there, and that's 100, and that's 1 over 100, and you get 0.01. And then you get 1 over R2, which is 50 ohms, so that's 0.02. And you can add them all up, do that one at a time with your calculator, add them all up, and then you can take that figure and divide it into 1, which is giving you your inverse again. I mean, these formulas are really very clever. And you'll come up with your answer. Or you can go online and do a research on parallel resistor calculator, and it'll give you the spot where you fill in the resistors and say calculate it, and tells you the answer. Now,
I don't guess they'll let us do that on the test.
that is precisely what I was going to say. But if you're studying for the test, you will get problems like this and they will come up. And you can sit down and you can figure it out. And by the way, you cannot use your
phone
in the test. The reason is you can look everything up on your phone. But you can use calculators.
With cleared memory.
Like this.
So are there scientific calculators that do these things?
Yes. But I'll tell you, my recommendation is you get a 4-function calculator, a really inexpensive calculator to take to the test. Your phones and my phone has, I mean, I can do all of this.
But don't we have to do imaginary numbers on some of these calculations?
Yes, but they are in such a form you can see the answer in your head.
Oh.
There are no tricky questions, except for those who refuse to study.
What? You look at me.
Well, you can be looking at me, don't worry.
There are no tricky questions on the test, and the answers are all out
So
there
some of them you
already.
just remember the answer.
So, you know, if you're really hung up on this kind of stuff, in the worst case, memorize it. But of course, the purpose of this course is to teach you how to use this stuff. But you know, if you get hung up on it, don't worry about it. Just continue hanging in here and learning. And you know, if you're say preparing for your technician license, I'm telling you a lot of stuff that's not on that test.
Yeah.
But it's generating your mind so that when you take the class, you will go, oh, I remember that. And oh, now it makes sense. Because if you go over something once, yeah, it's not going to be there. You go over it twice and you go, well, I kind of understand that. You go over it 3 times. Oh, this is starting to make sense. Get the idea? Just keep it up. Now,
So will R always be a positive number? I mean,
resistance?
yeah.
Yes. Yeah. Yes.
Yeah, I mean, I don't
I'm
have
going
any-
to polar coordinates and trying to remember. Yes, R is always a positive number. I think.
Because you're generating heat, right? Isn't that the point of the?
Yes. Yes. After Daron is over with, we're going to talk about decibels. Now, decibels are something you need to understand. See these formulas here? I want you to memorize them and be able to use them next time we come here. Now, don't write that down because I'm lying to you. I honestly, I've probably used these formulas once or twice in my entire life. I use this, and we'll go into this in detail after Daron, and we'll go into it next time. But 3 dB is just double the power or half the power. And once you learn it, you're on. So it's time for us to take a break. And when we return, Daron will be on. Sorry, Daron, I hate to do it to you. But
No, he doesn't.
So long as you direct me, Joe, I will follow your instruction.
Okay. All right, let's take a break. Have at it, Daron.
All right, what do you want me to do, Joe?
Well, let's see what I don't remember. I sent you a thing earlier today.
Yes, I have a 47, a 20 and a 10. And your diagram or your instructions had a 50 and I don't have a 50 ohm resistor.
Oh, well, yeah, 47 is the 50.
Okay,
So what, I think we did them in series first, right?
all right, let's build that. Thank you for making these really small so that my eyes
Yeah.
struggle.
Well, notice I put them in bags and I wrote big.
I appreciate that. That helps me a lot. Do you want any power on these yet, or are we just going to measure resistance?
Well, right now we're going to measure resistance, but then we're going to apply power and measure the current.
Okay, so there's our 47 ohm. And I will add the 20 ohm in series with it. And then we'll take this little teeny 10 ohm.
And did you forget to bring your?
No, I brought myself. Sometimes from you just looking at it.
So are we supposed to be building this as he does?
Yeah,
Really?
Don't tell me that.
Yeah, I know.
Yeah.
no, I thought that was just understood information. Listen, so you guys can see and do and learn.
So I don't have a diagram for that since I didn't make that, but we're just putting these three resistors in series down here on the lower part of the board.
Yeah, and so you've got a 47, a 20 and a 10, right?
Correct. So here's a 47. It's a magnetic screwdriver, huh? A 20 and then a 10 ohm. And I've just chosen rows here, columns. Which are these? I always get this mixed up.
Left to right is a row and up and down is a column.
Okay, so they're in the columns, they are hooked together. So we have one resistor hooked to another resistor, hooked to another resistor, so they're in series. Not a very good pointer. I should have got a better.
But you know, it's in the reason they're magnetic is because those wires are not copper. They're
Does it matter
tin
what
steel.
order we do these in?
If you do it 47, 20, 10, it'll be easier to sort out when we go to do things.
They all look the same.
Yeah, but see the
You know, yeah, I know, but
well, you
how
could,
will I return them?
yeah, honestly, I have to use a magnifying glass so I can see the colors. And instead of 50 ohms, we got a 47 ohm. Yeah, if it's a 10% resistor, 47 ohms is close enough.
Okay, 47, 20. Oh, but you know, after I have to bring my meter.
Oh, there's
Did you never come up with a meter?
No, I did. I found it. I just forgot to bring it.
Oh, so you do have a meter.
I do have. a
I've
meter.
got one
Yeah.
for you if you wanted it.
Yeah, no. Oh, no. I have
Okay,
to-
so that
It's got everything but a soldering iron. So one.
that first one's 47 ohms or pretty close to it.
What column does that go in?
Whichever one you want. I have it
They
in
have to be
4.
all in the same column, right?
All right.
I have the start of 47 in 4, 5, 6.
You have to. be in the
This
same-
one, and then this one, and then the next one is in the next group.
Oh, I see.
That'll put them in series. And to check resistance, you turn this to ohms.
And the next one is a 20 ohm resistor, and that looks good.
Boy, those are pretty accurate. They've been within 1 point each one.
And the last one is a 10 ohm resistor. So we'll look at all three of those in series.
Yeah, let's, Darren, give them just a moment to,
Okay,
yeah. They're all concentrating back here.
I can hear them.
Uh-oh.
Oh, well, I'm getting something. Oh. In the right place, there we go.
Okay, Ann, what do you have?
Well, 77, and then it's kind of jumps. I must be not be holding it. And then
Yeah, the
77.689. And then
Yeah, that's not unusual. It's, you're talking about tenths of an ohm in the, just the amount of pressure you put on the,
yeah, that's what I thought.
So we're talking
Yeah, try not to.
47 ohm,
Is
we're
it?
talking 10 ohm.
So it should be
47, 10, or 20 and 10.
67,
that's what-
77. It should be 77.
Yeah.
So how is it that I
well,
get?
actually, if you do it in your head,
Knock your
50 plus
glasses off
20
there.
plus
Yeah.
10
Drop my
Yeah.
meter,
would be 80 ohms.
80?
But
No,
but
it
it's
should be-
47 ohms, so 77
No.
would be,
Yeah, so that's what I'm getting.
go ahead and hook it up, Darren.
Should be 100 plus 47 plus 20.
Well, where are you getting 100 from?
The first-
No, the first one's 47.
Oh, Joe's notes are incorrect.
Oh, well, Joe's just leading us astray.
Look at this.
Oh, heavens.
Look at this guy. R1 100.
Oh,
R2 Joe.
you must have missed a column. I mean, you must be
Oh,
off one.
Sorry, Darren. Hey, look at that. It's the 76.8 ohms.
Yeah.
We're in the ballpark there.
Oh, yeah.
Yeah.
Cool.
Yeah, it should be 77, right? It's 47, 20, and 10.
Yeah, 79.1.
I don't even have to carry anything and I can figure that one out. Good job. That's good.
Yeah.
All right, you want to do anything power wise with that, or you want to put them in series?
You mean parallel?
That's what I meant. Yes.
Yeah, at this point,
Okay.
we've done voltage dividers enough, so the one thing we could do is do the current, show them how to do current.
Should be 77.
Well, you steer me in the right direction for what you want, Joe, and I'll build it.
Yeah, let me.
Well, if you take the negative supply and hook it up to the one side of the resistors,
Well, I'm gonna have to get another jumper for that.
I think you got I see a jumper there for the,
Now try it.
It's on there.
Yes, I've got one for the positive side.
And that's-
We'll
yeah, but
spin
you'll
this.
need a line that you can hook into the.
Battery.
All right, there's the negative one jumped. And you want to measure current on this?
Yeah,
I don't know
So
what's
what did he
happening.
do? He stuck it into the left side of the 47?
yes.
Correct.
Okay,
That's the-
and
That's
Does
the
it matter
ground
where the
side.
other end of the jumper goes?
It goes to the negative, which should be in column 2.
You're getting it 47 point.
Who's in charge of the camera?
What?
Who's in charge of the camera? So that
Me.
we can, see. Oh, gosh, I barely, you show it and then boom, it's gone.
Well, you have to pin me. Otherwise, anyone else talking will make that switch to another camera, to their camera.
Okay, I'll just.
Somebody has to pin her because I don't think she has pin.
Yeah, she should. Up in the upper right-hand corner of my display where the multimeter is, you should have 3 little dots up
I
there.
think she's
Oh,
on.
current.
Yeah, I have 3 dots, but I don't get anything to,
And if you click on those, there should be an option to pin.
no,
It's a Chrome computer, isn't it?
yeah,
Yeah.
yeah.
Should still
Yeah.
be the same interface, though.
Yep.
No.
You should hover over it. You shouldn't even have to click on it.
It's all right. We tried before. There's no pin. It's okay.
Oh, maybe intersection of what I want.
Gonna burn up my my regulator at some point, Joe.
Well, that's only 63 milliamp,
It's warm, plus the LED.
a plus 20, or yours is 30, right? Well, that's 100 milliamp. That's its
Yep.
maximum.
Yeah, it's running at 97 right now.
Yeah.
67.
Okay, I must have done something wrong.
Oh, there you had to, yeah.
So we've just got all three resistors
So
as our
I
load.
have this one in the wrong place.
Oh, well, the problem is you do not have a power supply there.
Oh, I do. What do I do it? I
Well,
do.
you've got
I
to,
don't know what to do with
you've
it.
got to completely build it.
Oh, I see. Oh, well, I'll do that next time, or I'll do it at home.
But, well, just
I
so
don't-
you know,
I don't exact, I remember how we did it before, but
yeah, well, see what you did is you put, you,
like this one
You
doesn't
do
go
not-
there, right?
yeah, you don't put two things in one hole.
Oh, okay.
So you just put in this next hole
So it just
over
have to
here.
be in the same column.
Yeah, same
not the
column.
Same,
Correct.
okay, so something in this little thing is doing the connection.
Yeah, and what you would do is hook your end here to the positive lead, which would be the power supply.
I got power.
Well,
It's gotta
yeah, that's
be,
9 volts.
oh, yes.
Although you could just do 9 volts
as
and
opposed
figure it
to-
out,
As opposed to what volts?
5 volts, because
With the power supply, you drop it down from 9 to 5.
yeah. that-
All right, I'll make that a homework assignment. I'll figure that out. I don't wanna hook that up and leave it that way. Okay.
Darren,
Yes, sir.
when you do this from now on, let's just go ahead and use the big regulator, the 7805,
Okay.
because then we don't have to worry about
Yeah, it's getting pretty warm.
creaming that poor little guy. Chuck is just sitting here.
Well.
You're-
I'm being,
you're-
I'm
You're an
being,
expert already. I know.
no.
All right.
Oh, I see. I took those off. I should have left these things on.
Scott?
What I did wrong.
Just pull out the positive lead on the that one right by its finger, that one there. Yeah, and measure between it and the resistor with current.
Oh, okay. I'm trying to figure out, I don't use this very much. Let's see.
You know, I can get my resistance.
He's coming around. He knows I need it as well, so okay, I just watch you. Yeah, meter is crazy.
Yeah, this should be fine for low current.
That's okay.
This only when you're doing high current.
Yeah.
Need that. But you probably need to turn the meter on.
I'm not even getting my resistance. I'm not even getting the 77. I should have. I got 2 of them. They're not.
But I have a hard time seeing.
Yeah, you and me both.
Yeah.
They're in the right.
Yeah, no, you got them right.
But it's just maybe not in the hole. all the way.
Yeah, I think with some of them, it's.
Well, here, let's do it this way. Let's just test the
One
first
three.
first one.
Cool.
Three amps.
Should be 47s, right? And then the
And
second
then we go to the next one.
should be 67. It is, and the third one is what I'm losing it.
And that's because this is not in the right folder.
Well,
It was bent over.
yeah.
Because,
It's okay.
we've got.
That'll work.
I got
Five volts power supply. First of all, we're going I equals E over R.
That's
So 5 volts.
What's the matter with it?
I know.
And R is 79
14,
volt,
yeah.
79 amps.
This is crazy. It's
Okay. Five,
is my 10, maybe my 10's messed up. Because the first two were.
5 divided by 79.
Could be that the board's defective too.
Here, want to try
10.
another board?
I got
There's
10.
10.
There's 10. Go back.
It's a poor musician who blames his instrument.
What did he say?
Poor musician wants his instrument.
Yeah. You'll get yours, mister.
Yeah, I know.
78.
77, 78. I don't know what the, yeah, okay.
106.
Oh, it's really kind of.
Jumping everywhere. I don't know if that's the meter or the board or what. It's not the musician.
Hang in there, John.
Well,
Use my board. It works.
okay, I mean, I can try it, but I don't want to I got a whole bunch of.
Okay.
I get the idea. So powered,
Yeah, this goes in the negative and this goes in the positive.
yeah, red to positive, and that's gonna go here on the first row.
Yeah,
We using jumpers yet? I haven't looked at it, so yeah, we are.
you could put it up here. Oh, well, no, you can't. Sorry.
Yeah, I can. Put it in.
Oh, well, I got something wrong.
330 for what?
300.33 amps,
Yeah, that's 330 millimeters. Because it's,
and that's not right. Because according to what I calculated here, 5 divided by 79 should be 0.066.
Now we're jumping over to 3.
Here's my minus.
oh, you're,
Hey Darren,
the reason is because you're running 9
the
volts.
jumper's going from the resistor over to column 3, right?
You're not using the radio.
I've got it in 4, but you should have a jumper from column 2 to column wherever you start the resistors.
That's okay.
Yeah, I
Because I got that jumper.
That's what gets, that's the ground.
The jumper coming down here.
Oh, from-
So you have a
oh,
jumper
I'm-
from
oh,
2
I'm
to 4,
Sorry.
Okay,
Alexis, I
all
thought
right.
you were-
and then I'm going from 4 to 7,
Yeah.
Well, what's the volt, measure the,
7 to 10,
go ahead and take that off.
and then 14 or something there.
Well, we just measure the resistance.
I measure the voltage,
Oh, okay.
and I'm looking for voltage. Here we go. We're on voltage.
I should have had the series diagram up. I couldn't find it. Sorry.
That's cool.
But we're got to have a resistor to the next column. Down here.
Oh, this thing shut off.
So these columns tie the resistors together.
Sure.
And then the plus 5 volts goes with the jumper to the last resistor, whichever column you have it in.
Is your battery about there?
Uh-uh.
3 volts.
Yeah,
Boy, that's one bright light.
yeah. 5.03.
Oh, well, you know, you're talking, oh, no, you're at 80. About 80 ohms, right?
Yeah, yeah. 5 divided by 80, right?
Yeah.
Five divided by
79 is what you have.
79 equals 63.
Yeah, 63 million.
Yeah.
So it should look something like that. I'm going to drop my meter in series so we can measure current. Again.
Yeah, 63 milliamps.
Yep.
Your case 64.
Who's got 64?
You.
Oh.
63.7.
Now I'm an overachiever. I could probably turn the voltage up just a little bit, gain a little bit more maybe. No,
You trying to measure current? You're just, you're in the voltage. $342 million.
Something's beefed up. And I just haven't got enough light to see enough stuff.
Well, but you were doing it correctly. That's the main thing. Well, Darren,
yes, sir.
let's go ahead and put them in parallel.
Okay.
What did I have in my note?
Because you got it all figured out.
Parallel.
But well, get your,
Let me flip back to that. You had 13 ohms in parallel, but I think that was calculating with a 50 ohm resistor.
47. Yeah, well, yeah, but it's going to be within 10%.
I don't know if you realize, Joe, but I'm pretty much into precision, so
Yeah, right.
not really. Okay, there's 3 resistors in parallel now.
oh, are those the ones that you? Oh, no.
So they're all in the same column.
Oh, yeah.
Now, now I know that, oh, you've got the bigger regulator in there.
Get
Good.
your,
Yeah, even it's warm.
So are the resistors, you don't have them hooked up at all?
I just have them in parallel right now. Let's check the resistance before we do anything totally crazy.
Yeah, what did we calculate the resistance would be?
Well, you
You
calculated,
know how to calculate the resistance?
I do, yes.
Have
I've
you
been
figured
doing
it
my
out?
homework. No, I haven't figured it out, but I will just a second.
Which resistors did you have? A 40, a 47, a 20, and a 10?
that is correct. And this meter is not happy with that range, I guess.
We get a couple of capacitors. Yeah, okay. Let me see.
Now
You said it didn't make you-
We're having some problems here too, Darren.
Yeah, I don't know if that's just a function of the meter.
See if there's a number on them. See, right, that's how numbers confuse stuff. So anyway.
I saw you punch the range button.
Yeah, I was trying to get it down into just ohms, but still won't read that.
Well, switch down to just some other location and switch back to ohms.
I did.
Oh, you did already. Oh,
Yeah. Oh, well, it helps if I get it out of the current plug. There we go.
oh. Oh, here we go. Okay.
Yeah, ID10T problem, not
Did you come up with a value?
6
I
ohms
mean,
is
we
what it
just add
says.
them up, right? Because they're in series.
No, they're in parallel.
Oh,
They're in
you
parallel
know,
now.
oh, I can do that.
So unfortunately, I have to use the formula.
Wow.
So it was.
Well, you can
47
go online if you want.
Over 20.
Honestly, that's what I
One
did.
1/10, right?
As soon as you guys dreamt up imaginaries numbers, I quit. So
Well,
Well, yeah, but there's no imaginary numbers here.
yeah, it's whatever.
Trying to talk yourself out of it, huh?
So I show 6 ohms anyway.
Yeah, and that's about right. What did my calculations say?
You said 13, but that may have been based on 50 ohms.
Um,
1.7.
Shouldn't be.
oh, that was probably a 50 and a 20 and a 10. No, that was probably.
No, that was a
100.
100, a 50, and a 20, Joe. Sorry.
Yeah.
Okay, yeah. I was gonna say you couldn't be that far off.
Nope, nope.
I got 0.6.
The middle one.
0.6. Well, you're off by an order of magnitude.
Oh, am I?
Yeah, it should be 6.
What did I do wrong? I'm gonna do it again.
That decimal point's always in the wrong spot.
Yeah, me too.
Yeah.
Well, go for it. Can't do that in my head. No, what did I do wrong?
I tell you, everybody, I'm getting tired.
0.02.
I'm confused. if I-
Yeah, I see something down there on the floor.
Where is it?
So,
Right between the two legs.
I don't know what that is.
Oh, okay.
Well, the next thing we'd want to do is find out what the current.
Oh,
is.
yeah,
The
yeah,
next thing I
yeah.
want to do is find out where there's a beer.
Yeah.
Okay.
That's gonna be a lot of current. You want to try to hook that up to power with 6 ohms?
Um,
I don't know.
6 ohms and 5 volts. Yeah, that is a lot of current.
let's start over here.
No,
Okay, that's the other one.
well, actually, it
let's-
should be about 900 milliamp, but I don't know if our battery would put out that much.
No,
Are you
I know
using
my-
for,
My power supply
Power
would, but
supply?
that's a lot of current, yeah.
here, sure.
Take your hand off the box.
ooh. Yeah, no,
Wanna go from this point,
they're quarter watt
this
resistors.
row over to third row. You wanna go from this one. Is
The-
one,
the,
and then the other one.
10
is over
ohm.
here. Oh, okay.
With 5
2 or
volts
3.
would be.
Yeah.
A half an amp. And a half an amp times 5 volts is 2.5 watts.
See,
Let's not do this unless you want to burn it up.
Oh, I don't mind. That's the way I do things, Joe.
Well, do not do what Darren's doing.
Yeah, it's not gonna,
fingers don't work well.
I don't know if I can change the range on this. It's only 700 milliamps.
Have you got it in the right?
Thanks, Chuck. Oh, yeah, smoke. Well, we don't want to do that.
Oh, look at that.
Joe, I'm gonna need a replacement resistor.
Yeah. And put your thing on a piece of paper too. That's really helpful.
Yeah, yeah, wouldn't do that. Too much.
It's a smoke alarm.
Well, we had. If we had. Now, does everybody understand why I talk about watts
Mhm.
and the power of a resistor?
Mhm.
I mean, we took a quarter watt resistor, put it across 5 volts with 10 ohms, and that's a half an amp. So a half an amp times 5 volts is 2.5 watts in a quarter watt resistor. That's why it's smoked.
Yeah, that one feller got a little dark there. Not gonna be good.
Well, you smoked that one a lot quicker than the other one the other day.
Yeah, that one went pretty fast.
Well, you know what was happening the other day is that we were, we had that voltage regulator in here. And it would not let itself be turned up. I mean, it has short circuit protection, it has overheat protection.
Yeah.
It has
You
overcurrent
frustrated
protection.
with something, but.
So it was.
Did very well.
Oh, yeah, I was gonna say, I'm sure it looks like you got it going now.
Yeah, that's yours.
But do I have anything else on my list, Darren?
Yeah, you wanted to do the 47K voltage divider or something
Oh,
with it?
yes, yeah. Okay, everybody listen up.
Oh, 247Ks in series, sorry.
No, 470K.
Yes, sorry.
Now you guys don't have this value. We just need you to watch.
Okay.
Darren is taking two 470,000 ohm resistors and putting them in series, which is close to a million ohms.
We'll go.
And he's going to put 5 volts across them.
Excuse me, the battery connector.
And where does it get its 5 volts from?
The regulator.
Yeah, our regulator we got on there.
Oh, okay.
Okay, now
Let, do you have your meters in the?
this is the.
I'd like to go back to auto here with the meter, but I don't know how to run it, I guess.
Well, just shut it off or turn it on again.
That's a Windows thing, Joe.
Okay, slam the door.
Here we go.
940, okay.
942,000 ohms, 0.9 mega ohms.
And let's see, we need 100 ohm resistor. What are the words?
All right. So you want to put voltage to that and look at the middle of it?
Yes.
Okay. So we'll put a ground over here. No, that's the positive voltage. That's oops, sorry. Hang on. Let me just keep it straight here. Get this out of the way. We'll put the plus 5 volts over here.
Yep.
And we'll add the ground.
Well, like, see,
Shouldn't you do the ground first?
wouldn't that be nice?
No, it doesn't matter.
Okay. So there's our ground going to one side through the 2 resistors and then back with the positive.
Okay, now somebody want to tell me what the voltage should be in the middle,
In the middle. What is it?
at the, between the 2 resistors?
2.5.
72. Oh, no, sorry.
So it's 5, right? So how?
This resistor.
Well, these here meter leads are not so good, or I have something wrong. There we go.
Yeah. Oh, keeps moving around.
Oh, yeah. Well, you have to get it in the right spot.
Yeah.
Yeah.
Many of these locations look very close to each other, so
I tell you something, all of our eyes are getting old.
We don't want to talk about old.
There.
all right.
There you go.
2.43 volts. Now what,
Almost 5 volts all the way through there.
4.98, so half of that would be 2.47, but it's 2.43.
What's the percentage on the resistors?
Sure.
10% probably.
Oh, aren't those 1% resistors?
No, I just grabbed them out of my box. They're probably 10s or something.
Oh, okay. All right, well, notice that the resistance is about 2.5 volts. Yeah, John and Scott, I hate to interrupt what you're doing, but I want you to. I want you guys to see this because it's important. Darren is measuring the voltage divider and finding that it reads 2.4 volts. You know, we figured in our head it ought to be about 2.5, so that's plenty close.
Yeah.
Now, Darren, get your Simpson and measure that voltage.
Okay.
Now, I don't know if you people remember the Simpson meter, but it's an old analog meter. Uses an analog. There it is.
It takes up a lot of room. It likes a big room.
Yeah. So now we're going to measure the same thing. And there it goes. What voltage range are you on?
10 volts, so that is 1.4 that it shows there, Joe.
1.4 volts. And we just measured it with the digital voltmeter at 2.5 volts. What's wrong? Can anybody tell me?
Is it just the difference in the meters?
Difference in the resistance in the meter.
Meters.
Yeah, this meter is what's called a 20,000 ohms per volt.
Oh, you're kidding me.
So,
Should be 50.
Somewhere right down here.
yeah, this is,
Right down here, 20,000 ohms per volt DC.
yeah. So it's in the 10 volt range, which means it's 200,000 ohms. But when you put 200,000 ohms in parallel with 470,000 ohms, you no longer have 470,000 ohms. You've got something way, way less. So if you're using one of these old analog meters, you have to be very aware that it will very likely change the reading that you have if you're not reading something that's low impedance, like a power supply or something like that.
Hence the difference between the VOM and a VTVM.
Yeah, well, a VTVM is a vacuum tube voltmeter, which had a voltage, input impedance of 10 million ohms. Like what is that little gadget you got there, Daron?
Well, Joe, that's my miniature oscilloscope.
Oh yeah, I've got one of those.
He's got all the gadgets.
It's a cool little device for this. Not so exciting on DC power, but you know, we get to AC, it'll be fun.
So how many volts do you have?
Oh, I don't know.
Yeah.
I don't know how to work it, Joe. I need your help.
Well, it's too small for me to read.
I can make it do pretty picture right there, 5 volts per division.
Oh, okay.
And we're right up there at 5 volts.
Yeah.
Yeah, okay, well,
One division.
stick it on the middle.
Looks a lot better on AC, sorry. 2.5.
Oh,
Yeah.
Yeah. there you
Change
go.
that. There's 2 volts per division, so it's just above 1 division.
excellent.
So let's see, when you have a device that has a high input impedance resistance, it has little effect on the circuit. But if you have something like that old Simpson, which we all used to use,
Still do.
and yeah, we've got at least one person who does, it can grievously affect the voltage that you're reading if you're not aware of what's happening.
I think my Simpson is a 50,000
ohms per volt. Well, that's one very sensitive voltmeter. So, when you're talking about voltage dividers, here's another thing that you need to be aware of when you're doing it. So fortunately, most of this will have digital voltmeters, and they have 10 million ohms per volt. And most of our oscilloscopes have 10 million ohms per volt input, like Daron's little one that he showed us. Although if you use it times 1 probe, then it'll be 1 mega ohm input, and that would change the voltage.
Very good point.
So anyway, how are we doing on time?
You're 20 minutes after.
You got 9 minutes.
Okay, well, Darren,
Thanks, Joe.
thank you.
Thank you, Darren.
Appreciate it, Dan.
That was really helpful. So we're, hopefully we're learning some practical stuff here, so that when you're out in the field trying to figure something out, scratching your head. And you know the kinds of things to use and what not to use, and what effect if you have the wrong kind of meter. You know, you might say, I need a voltmeter, and somebody will hand you an old Simpson. If you're checking a battery, it won't make any difference, but if you're checking at a voltage divider, like we're talking about, where you've got two 470K resistor series, it will have a major effect on the
That
voltage.
was as well.
Okay, so we're talking about dB. I made the mistake and put a small b here. Should be large B. But what we're talking about are the ratios of power, or the ratios of voltage or audio sense. And they're two different things. I'm going to back up. I'm going to try to back up. What's the matter? The power one is dB is equal to 10 times log of the power 1 over power 2. The second one, which is for voltage, is 20 times the log of value 2 over value 1. We like to think of that as voltage. If you're when we're working with dBs as an amateur radio operator, most of the time we're talking about power. If we're a QRP guy, we might be running 10 watts. If we add 10 dB to that, that makes it 100 watts. You know, if you take the power and you just double it, that's 3 dB. If you then double it again, that's 6 dB. And if you double it again, that's 9 dB. If you actually make it 10 times the power, but let's start out. If you start out with 1 and you double it, that's 2. If you take that double, it's 4. If you take that double it, it's 8. If you just take the original and multiply it by 10, that's 10. That's actually 10 dB. So if you've got a 100-watt transmitter and you increase its power by 10 dB, you're going up to 1,000 watts. That's something that we're going to, don't worry if you don't get this tonight, because we're going to go over this in more detail. If you notice this meter, which is upside down, that's a meter typically you find on the input or on the face of a amateur radio HF rig. And you can see from 1 to 9 S units on the very bottom scale, because it's upside down. So if you go from 9 down to 8, which is the mark between 7 and 9 there, that's 1 S unit. Well, 1 S unit is actually 6 dB.
That's pretty amazing.
So if you stop and think about it, if you go 12 dB, that's S7. Now, those of you who have operated on HF, there's not much difference between an S7 and an S9 signal. You can just barely tell the audio level between those two. But that's 12 dB. 10 dB, if you were running 100 watts, you would drop to 10 watts. So This is for those people who are for QRP, low power operation. It's not necessary to run high power. But I'm a QRO guy. I hate to admit it, but I would just as soon run a 1,000-watt linear. But that's just because of my personality style. Let's see. I
But
need,
isn't that the scale that you use to test your antenna with? Is it, do I have that SWR? SWR, isn't that the scale?
that's the next scale. This scale right here
Uh-huh.
is
Oh,
the
that's a,
S9 scale.
oh,
The
I
next
see.
one down is the SWR. And then this is the power output.
Oh, okay,
Oops.
got it.
So I'm trying to get back to myself. Any questions about anything we've talked about tonight?
Yes.
I had a
I'm
question,
going to close
Joe.
up and then I'm going to start working on Ann's question.
Joe, I have a question.
Go ahead, Don.
Isn't a dummy load basically a big resistor?
That is exactly right. It's
Yep.
a non-inductive resistor.
Okay,
Yeah, and I've got, I have two here. I have 100-watt and I have 1,000-watt.
yeah, I've got the 1,000-watt.
Yeah, and I've got the same thing at home. The one I've got here is good to about 500 megahertz. The one I've got at home is good to a gigahertz. Both of them.
Yeah, mine's actually mine's a 1.5K.
Oh, good, good.
Little one. That's the ground.
Any other questions? No? Well, God bless all of you and thank you for being here tonight.
Thank you, Joe.
Thank you, Joe. Thank you, Daron.
Thank you.
Thanks, Darren.
Yeah, Joe, I've got to work on one of those unanswerable questions for you. So every time you pose that, I got to come up with something that just is a real challenge. Thank you, my friend, for sharing this. This is very good stuff, and I love to put stuff together, measure, burn up, whatever it is. For me, that's the way it works.
Oh, that's such great fun.
But you have to forgive Darren, because to him, current is the thing that's followed as your ice cubes swirl around in the glass.
That is correct.
Ebb and tide. Night, everybody.
Great day.
A little of it. Oh, yeah, there we go.
Very nice, Joe. Thank you. It was awesome.
Yeah, well, good night, everybody.